Morning, everyone. My name is Jeremy Marshall. I'm from Clarkson University, and this summer the work that I did here at Penn State is all about hierarchically structured materials for energy storage. Now, as we explore this concept, we're going to go through a few checkpoints. Here are those checkpoints. First, we're going to talk about something called the energy demand, followed by an answer to that demand. Next, we'll talk about something I like to call a disorganized core network, followed by freeze casting, our plan for this project, and in the interest of time, please feel free to ask me about the project or the progress for this project in the question and answer portion of this presentation. The energy demand. So we have portable devices and electric vehicles. Portable devices including, but not limited to, of course, our cell phones and laptop computers. All of these things here listed on this page are devices that have experienced great technological advancements over the past few years. And because of these advancements, these devices now require more energy in order to function properly. And all of these devices run off of batteries. But there's a little problem. These devices here all have space restrictions. Our cell phones can't be this large anymore. Laptop computers can't be this large. And in cars, there are space restrictions. We kind of need room for things like, I don't know, wheels, and an engine would be good too. So all of these things need more energy, but the batteries need to remain small. Okay, here's a question. How can we increase the energy storage capacity of our batteries for these devices without increasing their size? We can do that by possibly thickening the electrodes in the batteries. Now, all of these things that I showed you on the past page all use lithium-ion batteries in order to function. What we're going to do right now is build a lithium-ion battery. So we're going to start off with our casing here. We have the negative side, the positive side of our battery. Next, we're going to drop in a couple of electrodes. Here's our negative electrode and our positive electrode, anode and cathode. Each of these electrodes have electrons and lithium ions. Next, we drop in our polymer separator. What this does, it prevents electrons from moving from one electrode to another while allowing lithium ions to move from one electrode to another. The lithium ions move from one electrode to another, and the electrons are forced to move through the external circuit, creating current that is used to power the electronic devices, such as what I have in my hand here. Next, we drop in our electrolyte. The electrolyte then seeps into the pores of both of our electrodes, and what you can see are little bits of white space. That white space represents areas that have not been touched by our electrolyte. The electrolyte is significant because the lithium ions can only move through the polymer separator if the electrolyte is touching a lithium ion. Any lithium ions that exist in these white areas cannot move across the polymer separator. That's energy that can't be used. This isn't really, really bad because we only have just a little bit of white space, just a little bit of material that's not being used. It's not a huge problem. Now, after we've added our polymer separator, our anode, our cathode, we add in our steel spacers. They're conducting. They're there mainly just to keep everything in place so that when we use our devices, our battery doesn't fall apart. Now, if we were to thicken our battery electrodes, we'd have something like that. We have simply more white space. As I said before, the electrolyte can only penetrate each electrode up to a specific distance. Adding material beyond that distance is just a waste. We're just adding more white space to our material. We're adding more material to our batteries that we can't even use. Okay, here's another question. Okay, why doesn't the electrolyte come in contact with all parts of the electrode? Okay, it's because the electrolyte can only penetrate each electrode to a specific distance. That distance is determined by the core network inside of each of the electrodes. Here's one of the electrodes, the material that our electrodes are made out of. If we look at it, this is what we'd see. But if we were a microscope and we had incredible eyes, we'd see something like that. Ladies and gentlemen, those aren't French fries, those are pores. And what you can see is some pores start at the top, they come partway down, some pores start in the middle here, don't really go anywhere. Another pore starts at the bottom, it doesn't really travel very far. What you won't find, and I bet you $20 you can't find it, is a pore that starts at the top and ends at the bottom. That's that's a problem because the electrolyte needs to travel through these pores. The electrolyte cannot reach the end of our electrode material because there isn't a complete channel for the electrolyte to go through. But if we had it set up like this, our electrolyte could be able to go through the material. And that way we'd be able to use that extra material that we add to our batteries. Oh my gosh, this PowerPoint has so many questions. How can we achieve an organized pore network? That's a great question, Mr. PowerPoint. We can achieve an organized pore network through something called freeze casting. Freeze casting is a 3-stage process that can change a slurry into a solid material with organized pores. And that slurry is just a solvent with particles that are well dispersed throughout that solvent. Those particles that I've mentioned are what we want our electrodes to be made out of because eventually that solvent will disappear, and we'll talk about that momentarily. 3 stages of freeze casting are the freezing stage, sublimation stage, and the sintering stage. Now, each of those stages have specific conditions that need to be met in order for this process to work properly. In our freezing stage, that specific condition is directional freezing. We want to freeze our slurry, so we get a mold, just a container here. We add our slurry, and then what we do is that we add a cold plate to the bottom of our mold. That cold plate sucks out the heat energy out of the slurry, causing it to freeze. That cold plate only exists at the bottom of the slurry, so heat only escapes from the bottom of the slurry. Heat only escapes from one direction, directional freezing. Now, the type of frozen structures that form in our slurry depend upon the solvent that we use. When we make slurries in our lab, we have one of 2 choices, water or tert-butyl alcohol. Now, again, if we were a microscope, we would see these well-dispersed particles throughout our slurry. These particles are important because of how the structures form, and you'll see why in a second. Now, tert-butyl alcohol. What happens when tert-butyl alcohol freezes is that these little lumps start to form in our slurry. The liquid slurry starts to solidify and forms these little lumps at the bottom of our slurry, and these little lumps start to grow. And they start to grow, and they start to grow and grow. And as they grow, they push away particles, those well-dispersed particles that are in our slurry. They push those particles out of the way. What you end up with is that. These columns have formed, and they push particles out of the way. And here is just another view. If we looked downward at a frozen slurry, this is what we'd see. We'd see those columns sticking up, and the particles closely packed between all of these columns. Here's just another view of just those columns that are formed if we looked at the side of our frozen slurry. Water does a very similar thing, except instead of columns, we'd see walls. If we look down and see these walls, these sheets of ice that have formed in our slurry, and that have packed particles together in between those walls. Here's just another view of those walls from the side. Now, in our freezing state, we use a dewar filled with liquid nitrogen, so cold that it boils at room temperature. Liquid nitrogen will suck the heat out of this copper rod, which in turn takes the heat out of this mold holding our slurry, and then the slurry freezes. That's how we freeze our slurry. Now, the sublimation stage. Sublimation is a process by which a solid goes from the solid phase straight to the gas phase. The sublimation phase or stage is very important because that is how we get those pores that I've mentioned before. We take our frozen slurry, we place it into a vacuum chamber at a temperature as low as -15 degrees C, and those columns or those walls of ice, depending on the solvent, start to disappear. And what we have left behind are just empty spaces. Those empty spaces are our organized pores. Once the solvent is removed, we no longer refer to this as a slurry. It is now our monolith. After we have sublimated our slurry into a monolith, we then put it through a sintering stage where we put the monolith into an oven at about 450 degrees Celsius, and we heat it, and that allows for this structure, these gaps that are formed, to strengthen and stabilize. So, all together, our plan is to use freeze casting on a slurry, freeze it. Hopefully we can get those pores that we're looking for. And to make sure that we've gotten those pores, we're going to take our monolith and put them into a scanning electron microscope. Afterward, we're going to fabricate electrodes and test them in batteries. Altogether, at the end of this project, if we can thicken those electrodes and give them organized pores, we would have been able to successfully restructure a material for greater energy storage. I'm Jeremy Marshall.